All right, before we get into conservation of momentum problems involving collisions and explosions, we have this quick section on rocket science. So we're now in a position where we can derive the rocket equation and understand the basic idea behind how rockets work. So we'll be able to answer this question. So we want to launch like a rocket into space. And actually, we want to launch it at the escape speed. So assuming you want to get up to this escape speed from rest and assuming a certain exhaust speed, so this is how fast fuel comes out of the rocket relative to the rocket. So that's a constant, but as the rocket starts moving, then the exhaust speed relative to the ground is going to be changing. But relative to the rocket, it's always the same. So assuming those two numbers, how much fuel would you have to carry? So in terms of the mass, like would you need double the amount of mass, triple the amount of mass, etc. Okay, so we'll be able to answer that pretty quickly. So let me draw a before and after picture. So the way that we're going to go about deriving an equation is by setting up a differential equation. And a differential equation involves differentials, which are small changes in quantities. So I'm going to draw a before and after picture, but the after picture is like a very, very, very tiny amount of time after the before picture. Okay, so infinitesimally, you can imagine like it's delta t, and we're going to take the limit as delta t goes to 0. Okay, so the before picture, and this is going to be all in the frame of the ground. In the frame of the ground. It's never a bad idea to specify, because actually this book makes these pictures kind of confusing. So I'll go back and talk about these pictures that the book have after we talk about, because they have 3 and we're only going to draw 2 pictures. So I want to tell you which 2 are relevant from the book. So in the frame of the ground, we're going to focus on the rocket when it's already moving at some speed. Okay, so it's going to the right at some initial speed v. So the initial momentum is equal to the mass of the rocket at that moment. So the mass is actually going to depend on time, times the velocity of the rocket. So the after picture is going to have, so a little bit of the mass of the rocket is ejected. Okay, so this little dot is how much mass came out. So the rocket has some final velocity. So I'm actually going to remove the p. So it has initial momentum mv. The final momentum of the rocket it's going to be a little bit less mass. So your book calls this delta. Delta is the small amount of mass that was ejected. So there's a little bit less mass, and we're moving at a little bit bigger velocity. And actually, we're trying to keep track of how much more velocity there is. So that's the dv. So v was the initial velocity, dv is the additional velocity picked up by the rocket. And then the ejected mass right here, so it could be traveling to the left or the right. We actually don't know. It depends on what stage of the rocket it's at. But it has momentum delta, because that's the amount of mass of that little, the ejected mass. So that's the mass of that stuff. And then the velocity is going to be whatever velocity the rocket originally had minus v naught. So it depends what stage of the rocket's firing, whether this is positive or negative. So like when the rocket is first starting out, this was 0. And so the exhaust velocity is moving to the left, right? So if this is 0, the exhaust velocity is moving to the left. And that's taken into account here with a minus sign. Okay, so this is the momentum of the ejected mass. Could be to the left, or maybe the rocket's been firing for a while, and actually the rocket's moving at a speed that's bigger than the exhaust velocity. So this could be moving to the right. Either way, though, it's ejected to the left relative to the rocket and boosts the rocket to the right. Okay, regardless of the final velocity in the frame of the ground. So connecting this with your textbook, this picture on the left is the before picture in the frame of the ground. This is what your So Shankar calls this is the picture A. And then this is the picture B. And so picture C is something kind of different. Picture C is in the frame of the rocket, the after picture. So we could also do the before and the after picture in the frame of the rocket. The before picture would just be the rocket at rest. So that, I'm guessing that's why your textbook doesn't show that, because it would just be M just sitting there doing nothing. And then the after picture is exactly what this C is. So the ejected mass moves to the left with speed v0, and the rest of the rocket, m minus delta, moves to the right with speed dv. Okay. And then, so B, picture B, is picture C, but then boosted, looked at in the frame of the ground rather than in the frame of the rocket. So in case you're wondering what these pictures are all about. I'm only focusing on the frame of the ground because all the equations that we're going to write down are in the frame of the ground. All right? We care about quantity. We're going to care about the velocity of the rocket in the frame of the ground. All right? The velocity of the rocket in the frame of the rocket is always 0, so that doesn't really tell us much. Now the key here to solving this, so we have a picture of what's going on. The key here to solving this is using conservation of momentum. And the reason we can use it is that there's no external impulse. There's no external forces. Okay, so the rocket, so if you look at like picture C, the rocket was at rest. That's the system, the rocket plus the fuel. So if the fuel goes to the left, then the rest of the rocket moves to the right. But like momentum would still be 0 in this picture. Okay, so picture C, it's a little easier to see that like the momentum of the little mass carried to the left is equal to the momentum of the boosted amount. Okay, so we're assuming that gravity, so the gravitational force doesn't just turn off as we're doing this, right? We're firing this up, this rocket upwards. So the gravitational force is acting down. That is an external force. The impulse, so remember we introduced the word impulse, and your book doesn't talk about this, so it just kind of ignores what's going on there, but we can understand this in a little more detail. The impulse that the gravitational force imparts upon the rocket is negligible as long as you do this exhaust stuff quickly. So this is why under the list of assumptions, we're assuming that the fuel is quickly used up near the Earth's surface, so this final assumption. The reason for that assumption is that the impulse, which is integral of f dt, so if you look at the only external force acting on this rocket is the gravitational force. The impulse from the gravitational force is negligibly small the faster that this happens. So the faster you use up the fuel and get to the escape velocity, the better. And you can this should make sense intuitively, because you can imagine the rocket just kind of burning its fuel just to keep still, right, above the ground, like hovering above the ground, and the force from the exhaust would be mg upwards. So if it's just hovering, it's wasting that fuel, right? It's burning up the fuel. So the longer it takes to eject all its fuel, the worse off you'd be. And that's because the longer it takes, the more chance gravity has to impart an impulse downwards on this rocket. So you want to use it up quickly. And that, if that's the case, if you use it up quickly, then you can ignore the impulse on the rocket from the gravitational force. Okay, so you quickly use up the fuel to get to the escape velocity, and then the rocket goes off, and obviously you can't ignore the gravitational potential energy as you go farther and farther away from the Earth, but but you can ignore that gravitational impulse just to see what speed you get up to burning up the fuel. Okay, so the point is, that the momentum is conserved because there is no external impulse. Okay, so the equation that we can write down here is that the initial momentum is equal to the final momentum of the system. And the final momentum of the system is the sum of the final momenta of the particles comprising the system. So this is going to be the momentum of the rest of the rocket, the part of the rocket that's left, and then also the momentum of the ejected mass. Okay, so just so that we don't write something like this, we're going to write the delta after, as the textbook does also. And we're not going to insert a minus sign here. There will automatically be a minus sign if this quantity is negative. Okay, so the variables are going to take into account a minus sign if that ejected mass is actually to the left. Right. Okay, so this is the equation that we have to work with that will help us set up our differential equation. But that's the main physics. The rest of it is basically just math to derive the rest. Right. So let's expand out the stuff on the right. So we get mv equals mv. Let's see, there's 4 terms just for this, right? So let's write down those 4. mv plus m times dv minus delta times v minus delta times dv. So those are those 4 terms. Plus v times delta minus v naught times delta. And I want to remind you that, remember, v naught is the speed that the velocity comes out of the rocket. It's not the initial velocity of the rocket. The initial velocity of the rocket is v, and the final velocity of the rocket is v plus dv. So don't think of v naught as initial velocity. That's the constant. You just think of v naught as a constant. It's the constant velocity of the exhaust. The v is the initial velocity, and then the v plus dv is the final velocity. Okay, so we can simplify this a little bit. So mv equals mv. We can cancel out both sides of that part of the equation. And then we have a minus delta times v plus delta times v. So those two are going to cancel out also. So it looks like we have 0 equals m times dv minus delta times dv minus v naught times delta. Okay, so we're looking at infinitesimals. Okay, dv is a very small quantity, or at least in principle, we can eject a very, very small amount of mass that can only impart a small velocity to the rocket. Infinitesimals. dv is an infinitesimal. And actually, delta is an infinitesimal. So your book was trying to do you a favor by reducing the number of infinitesimals. Delta is an amount of mass that was ejected, but it's an amount of mass that will shrink to 0 if the dv and the time. Remember that we're imagining a before and an after where like the dt, the delta t, shrinks down to 0. And if that shrinks down to 0, then the amount of mass ejected shrinks down to 0 if you're emitting mass at a continuous rate. So the delta is defined to be a positive quantity. You know, the way we set it up, we use delta as some amount of mass. But in terms of the mass of the rocket is decreasing. So dm, where m is the mass of the rocket, dm is negative and delta is positive. So actually, delta is minus dm. So the mass of the rocket decreases, so dm is negative, and then with a minus sign, that's the positive amount that's the positive amount of mass that was ejected, delta. Okay. But as a result of both of these two things being infinitesimal, that means that delta times dv is negligible, compared to the other two terms. Okay, so this is why we talked about the binomial series a little bit. We want to get you used to terms in the Taylor series expansion and what order you are in the Taylor series expansion. These terms are second order in the infinitesimals, and you can ignore them. Okay, and it's not that you're going to get an approximate equation. It's that we're setting up an equation that's exactly true to first order in the Taylor series. So we're going to get an equation that's exactly true. I know that's confusing. That takes a little while to get used to. But you just have to see a bunch of examples, and then you can try and rework it, taking that into account, and maybe prove to yourself that it doesn't provide you any new info. Right? So the point is, we can ignore that, and your book explains this in a little bit. That dm is minus delta right there. That makes it Easy. So that means that 0 is equal to m times dv minus v naught times delta, but delta is minus dm. So it looks like we have, so that becomes a plus sign, but then moving it over to the other side of the equation, we get minus v naught dm is equal to m dv. This is a differential equation that we can solve by moving all the masses over to one side and moving the velocities over to the other. Remember, v is the velocity of the rocket, and v naught is the constant exhaust speed of the exhaust relative to the rocket. And we're going to integrate both of these. This is the initial mass of the rocket. This is the final mass of the rocket. This is the initial velocity of the rocket. This is the final velocity of the rocket. So this is minus log of the final mass of the rocket divided by the initial mass of the rocket. And then integral dv, so we can factor out the 1 over v naught. That's just a constant. And integral dv is delta v. So delta v for the rocket. Now, -1 times log, we can bring this to the exponent right here. Remember, a times log b is the same thing as log b to the a power. So this log of, this minus log becomes log of what's inside the square brackets to the -1, which all that does is flip the two terms. Right? So that ratio to the -1 power just flips the fraction. Okay, so this equals delta v over v naught. And so our final equation for delta v, this is the change in velocity of the rocket. It's the exhaust speed times log of the initial velocity of the rocket divided by the final velocity of the rocket. So your book mentions or makes explicit that it's the final mass that depends on time, and then you're starting with some initial mass of the rocket that's constant. Of the rocket plus fuel, right? It's the mass of everything. So that's exactly the equation that we've, and I used, that's in your book. I used I for initial, because it's a little confusing that with the knots, with the zeros. Because m naught is the initial mass of the rocket plus fuel, but v naught just refers to the exhaust speed of the fuel relative to the rocket. So the zeros are kind of referring to slightly different things. So I think that can get confusing reading that equation. Okay, so for our example problem, we just need to plug in some numbers to find out what the mass is here. Okay, so for our original problem, this video will actually be maybe just 20 minutes for once rather than 30 minutes. For our original problem, we have delta v is the final speed of the rocket minus the initial speed is 11.2 kilometers per second. The exhaust speed is 3.0 kilometers per second. And what's the mass here? The rocket has mass m without any fuel. So that's going to be the final mass, right? That's the initial mass is going to include all the fuel. So it's the final mass that's just the mass of the rocket without any fuel. Okay, so we're going to solve for m initial, given that m final is just m. Okay, so, and we're going to solve for m initial, which is the rocket plus fuel mass. Okay, so plugging those things in, it looks like 11.2 kilometers per second divided by 3.0 kilometers per second. I didn't even write the units because they cancel out when you take that ratio. Equals log of m initial divided by m. So m is a parameter that we're allowed to use in our answer. M initial is what we're solving for. So if I do so if I do 11.2 divided by 3, and then e to that power, e to the 3 point something power, I get m initial is 42 times m. Huge. So the rocket plus fuel is 42m, so I need 41m fuel to get this rocket up to the escape velocity. which is crazy. I mean, at the beginning of the video, I said, you know, is it twice as much? Is it 3 times as much? It's 41 times as much. It's a lot, and it's all because of this log and the fact that it's, you know, this is a exponential, right? E to the power of the ratio of the delta V over V naught. That's the ratio of the masses. So that number can grow. I mean, it grows exponentially by definition. So you need a lot of fuel, is the point. And this is exactly why when you look at these huge rockets, actually most of that mass, the great majority of that mass, is fuel that's burned off. So that's why you burn off this fuel, and then you just eject that container to keep the important part of the rocket, which is called the payload. Yeah, so you might hear payload mass. That's the part the mass that matters. You know, that's the non-fuel stuff. Okay, so now you know rocket science. Next video, last video of the chapter, we'll do all the collision style problems. All right, great.